brought up the question of what interactions could do to 3D TI surface states. So let's imagine that this surface theory is subject to some interaction, and let's try to address that. This problem cannot be addressed unless you have a single particle basis for the surface theory, for which you can formulate exact ionization. And in the paper reference that I gave you, we provided the first exact ionization framework in which you can study interaction effects on a 3D TI surface. And that's what this study actually is good for. So let me summarize, and we have unfortunately been a bit quick in the end. We started from Lambda levels deeply appreciating guiding center variables and cyclotron variables in the plane. And I have been a little bit short on the sphere for massive electrons, but I think you could get the main picture. Now, with this at hand, we transferred the problem to a seemingly unrelated case, namely a 3D TI surface. But as we look hard enough for the same geometry, we find that we can recast the problem of Dirac fermions on the sphere as a baryon-flux problem, with a baryon-flux taking opposite signs for upspin and downspins and taking the absolute value of a single Dirac flux. That is the true story. Thanks, Ronny. Eigenstates. These spinor coordinates are just way more convenient to write down the eigenstates for the angular momentum operator, for the rotor Hamiltonian operating on the surface of the sphere. Since the spherical harmonics is a complete basis, you can, whatever you want, you can recast in them, but the question is it simple or not?
I think the question was even a bit more basic than that, was this a statement that you need to use the monopole harmonics, which are not single value in the sphere. Even if you wanted to use it, you couldn't use the spherical harmonics.
That is right. Yes. No. Okay. Okay. No. Sure. Yeah.
Yeah. So if that's true, then actually my question is, what's the physical consequence of that using monopole spherical harmonics? What's the physical difference between on a sphere with a monopole and playing with just
I don't think there's a significant physical consequence. The form invariance of the Hamiltonian that you get is showing you that reformulating on it on a sphere doesn't match off essential physics. It's just another geometry on top of which you can talk and understand lambda levels. The details that we get here, that we get into here in the lecture, they are really important when you have finite size realizations of the problem. When we go to the thermodynamic limit, which is to say we make the sphere infinitely big, of course, all descriptions sort of converge against each other. Okay? If the number of Dirac flux quanta is infinite, it shouldn't matter anymore whether the S naught is, you see, whether the S naught is half integer or integer. That shouldn't matter anymore.
I mean, just interject. I think one way of geometrically seeing why the sphere is different is what Ronny did was essentially steer graphically, pull the sphere back, pull the plane back on the sphere. But the minute you do that, you have the following problem. If I want to define the problem of the sphere, say I put it on the plane, you have a point where you have to choose a single location, say a flux, right? So if I think of the Aharonov-Bowman vector, right, quantum wave functions, there has to be a point where there's a singular flux solid. I have to see it in. Once I've done that, everything is okay. Everybody sees a uniform flux, and I'm happy. But the problem is, once I put that flux in there, when I wrap it back on the sphere, I have to remember where that flux went. That's roughly the Dirac string, the ambiguity of doing that. So when you pull back from the infinite disk to the sphere, you can't be single value everywhere. You have to have two atlases, right? And that's basically the same issue. The Dirac string is just telling you that piece of physics. You have a singular point. But it's just that once you've done it on the sphere, you can, in some sense, if you're doing something with a fraction quantum Hall effect or things where you expect fraction cases, the sphere is nice because you have a unique ground state. If you do it on the torus, you have multiple ground states and it's a thing to do. So in that sense, it's an important step because it allows you to sort of do finite size things without these other complications.
So changing the base mechanism doesn't change anything.
No, but on the infinite disk was the sphere, but the other, if you did any other thing, which is a compact manifold, you have to do the torus. That's the other simple one. And that's very hard to do. Because the reason the torus is hard to do is because of the fact that if you're looking for a topological chaotic phase, it has to be ground state, you've never seen the torus. So we want to look for unique ground state, which is presumably what Ronny is hoping for in some ways.
This is like, it's a very sophisticated answer. I mean, it's getting somewhere there where the lecture didn't go. I mean, if you don't know about the concept of topologigenesis and the genus of manifold, it wouldn't mean much to you now. But so let me just go back to this main message. I think we understood well the lambda levels of the plane of a sphere within the appropriate coordinates. The main story here is that you can think of a 3D topological insulator as having a very flux monopole in the center that gives a positive Dirac monopole to upspins and a negative Dirac monopole to downspins. And that interpretation, I think, is fantastic. That I think you can really carry on and like exploit more deeply.
So the change of phase.
Maybe we should continue. This is good. Looks like it might become a long discussion. So maybe discuss later. In case there's any other questions. Well, I have one. So this is what we will know. There's 5 universal classes of topological insulators. So is this one specific one?
Oh, this is the,
Does it know how to generalize the other?
Oh, this is the very specific one. What I'm talking about is the time reversal symmetry conserving 3D version of the quantum spin Hall effect.
Okay.
It was started to be realized in 2D, sort of the mother state of non-quantum Hall topological band structures was the quantum spin Hall effect. It was realized to be carried over to higher dimensions, and the 3D analog of the quantum spin Hall effect is this one because it shares the symmetries the symmetries that specify the symmetry protected topological phase. If you listen to sentence lecture, would be C2 from time reversal and U1 from charge conservation. Those are the 2 symmetries that you would look for. Yes, I have
one more question. One more.
So could you elaborate a bit about this Fermion sign, Fermion doubling problem? So like if we have these 2 infinite planes, like a naive way to understand that is that I have a drag cone up in the up plane and another drag cone down.
Okay, so let me take an intentionally simple-minded view. Let's just assume that I have a single cone on the surface. Okay. So if I go to the band structure models of the topological insulators, of course I would have the Fermion doubling problem. Because as soon as I put it on the lattice, I always have a mapping of high symmetry points. So I cannot have an odd number of Dirac species in the lattice model. That's the essence of Fermion doubling. The problem here goes a little bit deeper in the following sense. Imagine I start with a 3D model and I integrate out 1 dimension. What I would do is I wouldn't get a lattice model necessarily anymore. I would get a continuum. And in the continuum description, the Fermion doubling theorem doesn't necessarily apply. So you need the lattice regularization for it to apply. But there's another thing that applies that was done by Redlich, if you want to read about it, in 1984. Take a single Dirac cone, gauge it to a U1 field, then try to induce a gap on the fermions that allows you to integrate out the fermions, and look at the gauge theory that you obtain. What you will obtain is a half-integer Chern-Simons term that, as it stands, without anything else being there, is not gauging that. And that led Redlich to conclude that a single Dirac cone cannot be U1 gauged, for it cannot exist in even space or odd space-time dimension. So how is this problem avoiding the thing? And in field theory language, it's avoiding it because this vacuum of this topological insulator is non-trivial. Recasting the E dot B term in the appropriate way, it actually looks like global derivative of a Chern-Simons term with a half-integer prefactor. So in a very hand-waving, sloppy way, you gauge a single Dirac cone, you get half the Chern-Simons, plus the other half Chern-Simons from the theta term. 1/2 plus half is 1, it can be, it's consistent with gauge theory again. And if you want to read about the details on this particular point, there was a parity anomaly paper that goes through all the details of the calculation. It was done by Mike Mulligan and Fiona Cornell, I think 2013 or 14.
Let's take Ronny again.